All right, today let's talk about probability. Probability is measuring how likely something is to occur. If we look at all the possible outcomes of an event, that's called the sample space. That's key right there. You roll a die, a six-sided die. Then you can get the numbers 1, 2, 3, 4, 5, and 6. The numbers 1, 2, 3, 4, 5, 6, that is your sample space. The probability of getting, let's say, a 1 would be 1, because it's 1, 1 out of 6. But for equally likely outcomes, a theoretical probability of an event P of E. So that's the probability of event E. So you get the probability of rolling a 1, probability of pulling a red card. Is the ratio of the number of favorable outcomes to the total number of possible outcomes. Here's how I say it. Probability, it's what you want, over the total. The total, that's your sample space. What you want, that's your favorable outcomes. Odd number, red card, whatever you're talking about. But that's your probability. This is kind of like function notation, probability of event E. So we'll notate it like that for this class. First example, a jar contains 32 red and 28 blue marbles. Sample space, 60 marbles, right? What is the probability that a randomly selected marble is red? Well, how many are red? 32. How many marbles total? 60. I added them together. 32 out of 60. Simplify this to 8/15. Typically, we do write probabilities as simplified fractions. You may need to write it as percentages later, but for now, we're just going to use simplified fractions. A letter in the word restoration is randomly selected. What is the probability of selecting a vowel? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. How many of those are vowels? 1, 2, 3, 4, 5. That's probability. That's it. A day in the month of January is randomly selected. What is the probability of selecting a prime number? Well, for that, let's look at our sample space. Got a nice calendar right here. Maybe. So January has 31 days. And we want prime numbers. So it's going to be something out of 31. Or primes are those that, numbers that only have 1 in itself as factors. So 2 is prime, 3, 5, 7, not 9, 11, 13, 17, 19, not 21, 23, 25, 26, 27, 29, 2 plus count. Is that 15 or 10? Let's count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. Sorry about that. Counting's difficult. So I was remembering. I think I said 12. 2 dice are rolled. So we're rolling 2 dice and we're adding up the numbers. What is the probability that the sum of the 2 dice on the next roll is at least 9? So it'd be 9, 10, 11, 12, right? Now, we could write up the whole sample space, or we could just think about it. If we start writing down some things, we get at least 9. So things we can get is 12. That's 6 and 6. That's 12. Okay, we can get a 6 and then a 5, or we get a 5 and then a 6. Those are 11. For 10, we can get a 6 and a 4. We can get a 4 and a 6. We get 2 5s. That's the 10. So far, 1, 2, 3, 4, 5, 6 possibilities. How many ways can we get a 9? A 6 and a 3, a 5 and a 4. So the order does matter here. This is like separate. Yeah, 6 and 3, wake up here. 5 and 4, 4, 5, 3 and 6. 1, 2, 3, 4, 5, 6, 7, 8, excuse me, 9, 10 out of, well, 6 times 6 is 36, 36 possibilities. So it might help to actually draw out the sample space. We'll probably do that in class. But you can look at the sample space for rolling 2 dice. That'll be fine too. What is the probability of drawing a heart or a club from a standard deck of cards? So you need to know about your cards and die. In case that's just going to be considered common knowledge. If you don't know, go play some cards. So there's 1/4 are hearts, 1/4 are clubs. That's half. So there's 52 cards in a deck. 13 are hearts, 13 are clubs. That's 26. Applies to a half. Yes, I need to go back and simplify those. That one doesn't, this one does. 5/18. There are 8 books lettered A through H on the shelf. Scott randomly chose 2 books. What is the probability that he chose book A and B? All right, so it doesn't matter if he chooses A, then B, or B, then A, right? So how many possibilities are there? In fact, that's a combination. 8 choose 2. Okay. He chose 2 books. Excuse me, 1 second. All right, I'm back. So there's, the order doesn't matter. You get A, then B, or B, then A. So there's, take the calculator, 8, see, 2, 28 possibilities. And we're looking for one of those, A and B group. It doesn't matter if it's B then A or A then B. It counts the same either way. So that's 1 out of 28. There's 28 pairs of books you could choose from 8 books. So that goes back to what we learned previous days. The complement of an event is the probability of not happening, the opposite. So if you think about it, probability. We look at the sample space. All the possibilities, if you had the probability of every single possibility, it's got to be 100%, right? It's got to add up to 1. I mean, think about it. If you have either flipping a coin and getting a heads or flipping a coin and getting a tails, that's your only 2 possible outcomes. If you add those up, you get 1, 50-50, 1/2, 1/2. So if you add up all your probabilities, it's got to equal 1. So probably there's something not happening, which I'm going to notate it slightly differently than they do. They use the tilde here. I use a superscript C. Is 1 minus the probability of event E. Now this is a very important formula. Probably one of the most for probability. A lot of times whenever we have a complicated probability, we can actually think of it backwards and it simplifies it drastically. Let's look at some examples. Probability that it will snow tomorrow is 7 out of 20. What is the probability that it will not snow? Obviously not, Louisiana. What is the probability that it will not snow? 1 minus 7 out of 20, which of course is 13 out of 20. A month of the year is randomly selected. There's 12 of those, by the way. What is the probability of getting a month that does not begin with the letter A? Well, let's see. January, February. You could just do January, February, March, not April. So you could add all those up, or you could be like, there's April, August. That's it. So 2 out of 12 do start with A. So 1 minus that is 10 out of 12. Hoping I didn't miss any months. Let me just check the calendar real quick. January, February, March, April, May, June, July, August. So yeah. So you can count it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of 12. Either way you do it, you get the same result. We got this spinner here. Find the probability that it lands on a number that is not prime. So let's count how many primes there are. 1 is not prime, okay? So 1 is neither prime nor composite. 2 is prime, so that's 1, 2, 3, 4, 5, 6, 6. So there's 6 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16. Oh yeah, it's 1 through 16, so 16. So 6 out of 16 is how many primes there are. Minus that, 10 out of 16. 5/8. Okay. Again, we've got 2 dice being rolled. It says, what's the probability of not getting doubles? Well, getting doubles is easy. There's could get double 1, double 2, double 3, double 4, double 5, or double 6. And whenever it says dice or die, we're going to assume a standard 6-sided die unless it otherwise says, okay? So 6 out of 36, that's doubles, but we want not doubles. 15 out of 18. Which they all have 3s in them. 5 out of 6. All right, so let's continue by looking at compound events. So whenever we have multiple events happening, rolling a die, flipping a coin, anything more than one event happening, it's a compound event. Now the events can either be independent or dependent. If they're independent, then one event happening has no effect on the other one. If they're dependent, then the outcome does affect it. So independent, you flip a coin and get a heads. You roll a die and get 7. They don't affect each other. Dependent, you take a card out of a deck and it's an ace. You don't put that card back, you're changing the total number of cards, so the next card you pull will have a less total be out of. So that would be dependent. The probability of the event would change based on what happened at first. So independent events, probability of A and B happening is just the probability of A times the probability of B. If they're dependent events, then it's the probability of A times the probability of B, assuming A already happened. So we say B given A. And that's how we're going to refer to it. So it's a probability of B happening, assuming that A already happened. Card example. You pull an ace out of a deck. There's now 51 cards in the deck. So if you want the probability of an ace and the next card being a 3, well, then it's aces, there's 4 out of 52. Threes, there's 4 out of 52, but we took that ace away, so now it'll be 4 out of 51 for the B given A happens. Well, plenty of examples, so don't worry. A die is rolled 3 times. Well, let's see. Does the roll of the first die affect the roll of the second die? No. This is independent. What's the probability of getting 1s on each roll? So it's just the probability of getting 1 the first time. And if it doesn't specify, we assume a 6-sided die. Probability of 1 the second time and, the third time. Yes, you could have just done 1 over 6 to the third power or 1 over 6 to the third power. And either of those would work just fine. 1/6 raised to the third power is 1 out of 216. A coin is tossed, then a day of the week is selected. Well, if you flip a coin, does that change what day of the week it is? Unfortunately, no, otherwise it would always be Saturday and Sunday, right? What's the probability of getting a tails and then a day starting with the letter T? So tails, well, there's 1 tails, 1 heads, that's half probability. 1 out of 2. And days a week, well, there's 7 days and Monday, no, Tuesday, yeah. Wednesday, Thursday, Friday, Saturday, Sunday. 2. 2 of them start with T's. Type it in the calculator, you get 1/7. All right, so let's look specifically at some independent events. So an easy way to tell between independent and dependent is a lot of times you're going to be taking something and putting it back. That would be independent. Or you're going to be taking something and not putting it back. That would be dependent. So here, these are independent because we're taking the crayon and then we're putting it back. We got 8 red, 14 purple, 6 yellow, and 4 green. So if we want probability of purple, then yellow. Well, how many purples are there? 14. Excuse me, sorry. And there's 32 crayons, right? 28 plus 4 is 32. Yellow, there's 6 of those. Still 32. So you're going to take your calculator. (14 out of 32 times 6 out of 32. And that gives us 21 out of 286. We're going to leave it just like that. So these should not be bad at all. We just find the probability of the first, green, so 4. That's probably the next, red, 8. Multiply, simplify, 1 out of 32, right? Two purples, so we're going to get purple, then purple again. And these aren't changing because we're putting that crayon back. We're taking the purple crayon out. Yeah, we got purple. Putting it back in, taking another crayon. Oh, we got purple again. That 49 out of 256. Two yellows, 6 out of 32 times 6 out of 32. Well, that's 36 out of whatever the heck that is. Who cares? Just use your calculator. Nine out of 256. So if we have compound events, we just take the probability of the first event times the probability of the second event. If we have 3 of them, times probably the third event. So on and so forth till you got all your events done. Now, what if they're dependent? So we're taking a crayon and we're not replacing them. So I grabbed this because it has the numbers on it, but we're not replacing it this time. Not replaced. Yellow and then red. So yellow, okay, that's just probability of A, 6 out of 32. Times red. What's the probability of red? Was 8 reds. But remember, we didn't put that yellow crayon back, right? So there's now 31 crayons in the box or bag. So if we take the calculator, we'll get 6 out of 32. Wow, 3 out of 62. Purple, then green. Okay, there's 14 purples, 32 crayons. Greens, there's 4 greens, but there's only 31 crayons left. So take the calculator and just do it. Okay. 14 out of 32 times 4 out of 31. 7 out of 124. Okay, what's next? Let's see. So again, we're not replacing probability of 2 reds. So we pull a red, we don't put it back, and we pull another red. Let's see what that probability is. 8 out of 32. Okay. We took a red crayon though, right? How many red crayons are left? 7. How many crayons total? 31. 7 out of 124. Let's see the calculator. It's too late to be trying to think. Shoot calculator. So it's 4. Seven out of 124. Okay. 2 greens. So 4 out of 32. Easy stuff. But then there's 3 greens left, and there's 31 crayons left. So again, same thing. Wait, that's going to be different. Because, yeah, I have that in my head upside down. That's definitely going to be 248, huh? Just use your calculator. No reason to think. The calculator's 4, right? That's how you do it. You just multiply the things together. Yeah. Okay. So again, you gotta know cards. There's just it's common knowledge. You just gotta know it. Everybody's gonna assume you know how many cards are in a deck, and yeah, you just need to. Standard deck, 52 cards. We're gonna take one and not replace it. And we want probably a heart, then a spade. So hearts, well, that's how many hearts? 13, right? How many cards? 52. Times, we took a heart out. We did not put it back. So now we're down to 51 cards. How many spades? So 13. So 169 out of some large number. Yeah, that's not simplify. What does simplify? 13 out of 204. So if you do, for whatever unsightly reason, need to simplify this, you remember this is 1/4, right? So 1 times 13 is 13, 4 times 50 is 200 plus 4. Yeah, okay. So if you need to do this by hand for your class, I'm sorry. Some college professors just don't like calculators. But yeah, you definitely want to simplify that first and then multiply. Jack had 4 Snickers and 8 Mars bars. He randomly chose a piece of candy, ate it, then chose another. What's the probability that both candy bars were Snickers? So at first he had 4 out of 12 being Snickers, right? He had 4 4 Snicker bars, 8 Mars, 12 altogether, 4 out of 12. Then he ate a Snickers and wants to get another. 3 out of 11. So that's 1 out of 11, right? Calculator. One out of 11. Beautiful. So that's compound events, guys. I'm just going to stick this on the end of the other half of the video that I started yesterday. And we'll go from there. See ya.